In the next section, we're going to introduce the concept of gas exchange, basically describing how oxygen gets into the lungs, carbon dioxide gets out of the lungs. For the seventh section of pulmonary pathophysiology, we're going to talk about gas exchange. Begin to examine not only how air gets in and out of the lungs, but actually now how it starts to get out of the lungs into the bloodstream. There's some nomenclature that unfortunately we're just going to have to memorize. Luckily, this nomenclature is consistent. You'll learn it now in pulmonary physiology, but you'll use it again when you're taking care of patients on the wards. When we refer to a PO2, or a partial pressure of oxygen, we'll use nomenclature to distinguish whether that's the partial pressure of oxygen in the atmosphere, in the case of P atmospheric, whether it's the partial pressure in the alveoli, as in the case of P sub capital A, or the partial pressure in the arterial, P sub little a. Once again, this nomenclature will be consistent throughout your training. Remember when we talked about the airway zones? There was a difference between the pseudostratified columnar epithelium that we had in the upper airway and the squamous epithelium that we had in the lower airway. That upper airway represented the conducting zone. No gas exchange occurred. The only gas exchange happens in the lower airway, the respiratory zone, where you've got the squamous epithelium that are functionally designed to have not much distance across which the gas has to diffuse. So for each breath, some of our tidal volume will be in that conducting zone and therefore won't be able to contribute to gas exchange. This represents what's sometimes called the anatomic dead space. Additionally, there are alveoli that get ventilated but don't get perfused. The combination of this alveolar dead space and anatomic dead space is sometimes referred to as the physiologic dead space. Even though we're totally healthy and have functional lungs, some of our breaths get wasted on areas that aren't going to be able to participate in gas exchange. So if we try to quantify ventilation, we look at the air that comes in with each breath. We might sum that up over 1 minute, referred to as minute ventilation. Sometimes it's referred to as V with a dot over it, or V sub E for volume exhaled or expired. Our tidal volume is going to be the amount of air that we breathe in with each breath. We can look and combine that tidal volume times how many breaths per minute to get a minute volume. So our minute volume is the tidal volume times our respiratory rate, or frequency. Now if we think a normal breath is about 500 cc's, which is reasonable, and a normal respiratory rate, or frequency, is about 12, we can look at what our minute volume would be. 12 times 500 is about 6 liters, 6,000 cc's. But remember, this is just our total minute ventilation. It's not the amount of gas that's actually getting to the alveoli. If we want to know how much gas is actually getting to the alveoli, we have to subtract out that dead space, that physiologic dead space. So with each breath, with each tidal volume, there's going to be some dead space. We could take that total tidal volume minus the dead space, multiply it by the frequency. So if we had 500 cc normal breath, of that 150 cc's are dead space. The total breath that we're taking in would be 350 cc's that would be participating in gas exchange times 12 times a minute. So for a normal respiratory rate, we have a... Here's another question that's going to demonstrate this point. Let's assume that both Jim and Ryan are exercising and they've got the same tidal volume and respiratory rate at baseline. Jim is going to just double his respiratory rate, but he's going to keep his tidal volume exactly the same. Ryan, however, is going to double his tidal volume, but keep his respiratory rate exactly the same. So let's think about who's going to have a higher minute ventilation, and who's going to have a higher alveolar minute ventilation. So Jim doubles his respiratory rate from 12 to 24, but keeps his tidal volume the same at 500. his alveolar ventilation is going to be his total ventilation is going to be 24 times 500 or 12 liters, but his alveolar ventilation is going to be 24 times 500 minus 150 or 8.4 liters. Ryan, on the other hand, doubles his tidal volume, keeps his respiratory rate the same. His minute volume is going to be the same, 12 liters, but his alveolar minute ventilation is actually going to be higher. It's going to be 12 times 850, or about 10.2 liters. His dead space stays the same, so he's taking more efficient, deeper breaths. His dead space fraction is actually decreasing with each breath. Now, in truth, when we exercise, we increase our respiratory rate, we increase our tidal volume, and not only that, we actually decrease our amount of dead space because more alveoli get perfused. Reviewing this, remember we've got a conducting zone and our respiratory zone. The respiratory zone where gas exchange occurs, the conducting zone is going to contribute to dead space. But we need that conducting zone to humidify the air, to conduct the air down to the alveoli, and to allow for a place where particles can get trapped and cleared in the mucociliary elevator. Our tidal volume times our frequency gives us our minute ventilation. Our tidal volume minus the dead space times the frequency gives us our alveolar minute ventilation, which is going to be what's important to gas exchange. Disorders that increase our dead space are going to reduce our alveolar ventilation. We'll talk about that more later. Minute ventilation is a very important concept. If you have a disease that presents by a patient taking more frequent breaths or deeper breaths, they're needing to keep a higher minute ventilation to keep up. If the patient can't keep up with this, they'll go into respiratory failure. And if we need to support that patient with mechanical ventilation, we need to know what their minute volume requirements are. The air we breathe is a mixture of nitrogen, oxygen, and water vapor. There's really not much appreciable carbon dioxide in the atmosphere. The total sum of the partial pressures of each of these gases will equal the total partial pressure of the atmosphere. The atmospheric pressure is whatever the barometric pressure is. So that the sum of all the partial pressures, the partial pressure of nitrogen, the partial pressure of oxygen, the partial pressure of water vapor, all is going to add up to the atmospheric or barometric pressure. At sea level, barometric pressure is 760 millimeters of mercury. And this barometric pressure is going to decrease as we go to higher and higher altitudes. The partial pressure of oxygen is the percentage of oxygen times the barometric pressure. So at sea level, atmospheric pressure or barometric pressure is 760 millimeters of mercury. And we know that room air, ambient air, is 21% oxygen. Therefore, the partial pressure of oxygen at sea level is 760 times 21% or 160 millimeters of mercury. So the P atmospheric O2 at sea level is 160 millimeters of mercury. Let's look at what's going to happen to the P atmospheric O2 as we go to higher and higher altitudes. So we start out at Galveston. Barometric pressure is 760, 21% of that 760, the atmospheric O2 is 160. We go up to Denver, about a mile high. Barometric pressure is now 640 millimeters of mercury. The atmospheric pressure, 21% of that, is down to 134. All the way up to Mount Everest at 29,000 feet, where the barometric pressure is 253, the atmospheric pressure, 21%, of that is 53 millimeters of mercury. So the atmospheric oxygen on top of Everest is just 53 millimeters of mercury. The air that we breathe in travels through those conducting airways. During that travel through, it's warm to body temperature and it's fully humidified. Therefore, at 37 degrees and 100% humidity, the air is carrying all the weight of water vapor that it can. The partial pressure of water vapor is 47 millimeters of mercury. So if we look at the air that's in our trachea when we're taking a breath in or in our conducting airways, we're going to need to subtract out those 47 millimeters of mercury of water vapor so that the total pressure that oxygen will contribute to is 713 millimeters of mercury, 760 minus 47. So if we looked at what our inspired O2 is, the air that's in our trachea, 760 minus 47 is 713 times 21%, that gives us 150 millimeters of mercury. The atmospheric oxygen was 160, the inspired oxygen is 150. This question illustrates what happens as we go further down the airways. The partial pressure of inspired oxygen, PiO2, is blank compared to the partial pressure of alveolar oxygen. It turns out the partial pressure of inspired oxygen is greater than the partial pressure of alveolar oxygen. We'll talk about why in the next couple slides. There's two main culprits for this, two main reasons. A small reason that contributes to this is that some of the oxygen actually diffuses into the large airways. But a bigger reason why alveolar oxygen is less than inspired oxygen is that we have to account for CO2. When we get to the alveoli, not only is there oxygen, nitrogen, and water vapor, there's also a continual supply of CO2 that's coming back from the alveolar capillaries. This CO2 displaces oxygen in the alveoli. It takes up space. And the amount of space it takes up is governed by a correction factor, referred to as R or sometimes Q. For so much CO2 that's in the bloodstream, we're going to displace that much oxygen. That's going to lead us to a very important equation, the alveolar gas equation. In general and pulmonary physiology, there's not much you need to memorize. None of the equations that we've talked about thus far, Poussey's law, Ohm's law, the equations that govern surface tension, you need to remember for when you take step one of the boards. The alveolar gas equation is an equation that I would want you to remember, not only when you take step 1 or 2 of the boards, but also when you show up on the wards and when you take care of patients. The alveolar gas equation is important because it helps us to understand how atmospheric oxygen is higher than inspired oxygen and is higher than alveolar oxygen. And we're going to use this equation to calculate the alveolar to arterial oxygen gradient, which is important to defining diseases that affect gas exchange. The alveolar oxygen equation equals the atmospheric oxygen minus water vapor times the FiO2 minus the alveolar CO2 content divided by the respiratory quotient Q. Some of these numbers we can remember as constants. The FiO2, if we're breathing room air, is 21%, 0.21. In general, the respiratory quotient Q, or R, is 0.8. For the alveolar CO2, we can never really know what the alveolar CO2 is, but if we know what the arterial CO2 is, we can substitute that, because for all extensive purposes, the alveolar CO2 is going to equal the arterial CO2. So if we were at room air, if we were breathing room air at sea level, we could calculate our alveolar oxygen. 760 minus 47 would equal 713 times 21% minus 40, which is a normal PaCO2, divided by 0.8. That gives us a normal alveolar oxygen level of 100. Now remember, the atmospheric oxygen is higher than the inspired oxygen, which is higher than the alveolar oxygen. Water vapor contributes to the inspired oxygen being lower. Carbon dioxide is contributing to the alveolar oxygen being lower. Let's do this example on Mount Everest. We said the atmospheric pressure was 253 millimeters of mercury. What would the alveolar PaO2 be if a climber had a peak CO2 of 20? 253 minus 47 times 21% minus 20 divided by 0.8. That climber would have an alveolar oxygen of 18 millimeters of mercury. Remember, normally our alveolar oxygen is 100. What would the PaO2 be of the climber if her PCO2 was 30 instead of 20? If we did the equation in that case, her PaO2 would be just 5.5 millimeters of mercury. It would be just 5.5 PaO2. This is remarkable that we can climb Everest at all, and speaks to why most people that do it need supplemental oxygen. In truth, when climbers climb Everest, they actually blow their PCO2 down to much lower than 20, usually lower than 10. The PaCO2, the alveolar CO2, is going to be directly controlled by ventilation. So if we know what our minute ventilation is, we can figure out what our PCO2 is going to be. Let's do another example. Mr. Smith is a 68-year-old gentleman with emphysema. What is his alveolar O2, his PaO2, if his alveolar CO2 is 60 millimeters of mercury? Subbing in and doing this equation, we find that his alveolar oxygen is 75 millimeters of mercury. Just because his PCO2 is higher, his alveolar oxygen is lower. Because there's more CO2 in his alveoli, even though he's breathing the same room air that you and I are, his alveolar O2 is lower. Remember, alveolar oxygen is less than atmospheric, and the alveolar gas equation can be used to calculate the alveolar oxygen. Remember, the higher our alveolar CO2 is, the lower our alveolar O2 is going to be. That concludes our introduction to gas exchange. We've gotten air out from the atmosphere into the trachea and down into our alveoli.